Science Tutor at DUMFRIES House. Recently you might have heard more than usual about data and statistics. That's because data is really important to help scientists understand more about the world around them. Because of this, it's more important than ever that you understand what we mean when we talk about data and know what to look for in good graphs and potentially to spot misleading information. So that's what we're going to be talking about in this video. We will discuss what data is, how it can be collected and displayed, and we'll take a closer look at a couple of different graphs and charts and the kind of information they can be used to show. Data isn't just numbers. In fact, sometimes it isn't numbers at all. Data is just information about a subject, and our subject for this video will be trees. I'm going to show you how you can collect some information about trees and then convert that into graphs or charts to help you and other people understand what you've collected and what you've found out. Often, having lots of information about a subject helps us to understand it. So scientists collect data on subjects they want to learn more about. Data can take on two forms, descriptive or numerical. Numerical data is information about a subject in the form of numbers. Data based on numbers is called quantitative data. So a piece of quantitative data about this tree might be that it's 92 centimetres in diameter. A good way to remember this is that the word quantitative comes from the Latin word for having quantity. So if you have a measurable quantity of something, then it is likely to be quantitative data. Descriptive data is known as qualitative data. You know the saying quality over quantity? Well, when something's value cannot be summed up by its quantity, then we would look at using its qualities. So when the information you are gathering cannot be summed up using numbers, your data would be qualitative. An example might be wanting to gather information about how being around trees and woodlands makes people feel. You can't use data in the form of numbers to explain this, but it is still information. For the sake of this video, we'll be focusing on quantitative data and displaying the information we collect using graphs or charts. Observation is one of the most important skills that scientists have. We can use tools and equipment to observe and take notes on things and learn more about them. Scientists collect data because they have a question they want to answer. Our question is going to be, what kind of tree is most common near me? For this to work, you need to be able to identify a few common British trees. If you've not previously watched my other video all about tree ID, then please do check it out. Otherwise, if you're up to speed, you want to look for different kinds of leaves in the woodlands around you. My question is only about the trees local to me, so I've chosen to do my survey in a local park. The size of your survey area will depend on the kind of question you're asking. If your question is only about local trees, then you can pick a local area. If your question was about the whole of the UK, you would have to do a much broader survey to make sure that you can find the answer to the question you're looking for. You can use mapping websites or physical maps to find the right kind of area for your survey. So now I've collected lots of information about the trees in my area, so hopefully hidden somewhere in all this information or data is the answer to my original research question. To help me find it though, it's easier, rather than leaving the data in its raw form, the way I collected it, to convert it into a graph or a chart. This not only makes it easier for me to find the answer to my question, but also for me to share those answers with other people in a way that's clear and easy to understand. To convert my raw data into a graph or chart, I first have to organise it. In this instance, this means sorting my data into groups. I can either do this by hand or using a computer. Once my data is sorted, I can start building my graph. During my research for this video, I read that ash trees are one of the most common trees in the UK. I'd like to use my data to test this theory. Thinking back to my original research question, I'm interested in a particularly small part of my data in relation to everything else. I'm interested in the ash trees in proportion to all of the other trees I've surveyed. For this kind of data where you're interested in one part as a proportion of whole, the best kind of chart or graph you can use would be a pie chart. So we'll have a look at how to build one of those using the information we've collected. Pie charts are circles with slices of different sizes cut out like a pie, where each slice represents a portion of your data and all of the slices together add up to make all of your data. This means they're particularly useful when trying to compare one part of your data to everything else. We're going to use our pie chart to show how one part of our data, the ash trees, compares to everything else in our data set. There are two options for building your pie chart. You could either draw it out by hand or you could use a computer spreadsheet program like Excel to help you. If drawing your pie chart by hand, you'll need to do a little extra math to work out what size each slice should be. As a circle is 360 degrees, you'll have to work out how large each slice should be as a fraction of 360. To do this, take one of your categories, ash, and divide the number of data points you have for that by the number of data points you have overall. So 30 ash divided by 131, all of your data. This gives you 0.23, which you then have to multiply by 360 to complete your calculation and get 82.4. So, of the 360 degrees in your circle pie chart, just over 82 of them will be taken up by the ash slice. Do this for the rest of your data and you'll end up with a full pie chart with one slice for each category. To draw your pie chart, start with a circle on your piece of paper. Mark the centre of your circle and draw a line from the centre to the edge. This will be your 0 degree line. Now use your protractor to measure out your first slice. Line the 0 degree line of your protractor up with the 0 degree line of your pie chart, and then mark out 82 degrees for ash. Draw a line from the centre to the edge of your circle through this mark. This is your new 0 degree line. Repeat this for all of your measurements to complete your pie chart. With any chart or graph, making sure you have good title and labels is important. It can also be useful to colour code your chart to make some information stand out. You could also enlist the help of some technology, such as a spreadsheet program to help you out. Using a program like Excel, you can input your data in rows and columns, and then select this data, click on Graph, and create a graph of your data this way. Once you've got your graph, you can go into it to edit where the data is coming from. So don't worry if it doesn't look how you expected the first time round. As I said earlier, pie charts are used when we want to compare a part of our data to the whole. Some good examples I've seen online recently are the UK's energy fuel mix, which you can see if you go online. You'll be able to see what proportion of our energy comes from solar, hydro, or coal-based power. To collect my data this time, I need a piece of equipment called a clinometer. A clinometer can be used to measure angles and distances of objects too big or too far away to use a measuring tape. To make your clinometer, use a few common craft materials you have around, like paper, pens and scissors. Start by drawing a quarter circle in the corner of your piece of card. Try and line up the middle of your circle with the corner. Then draw a double-sided arrow along the top edge of your quarter circle, writing U at the side nearest the edge and tree at the side of the corner. Now find a 45-degree angle using your protractor. Line it up with the top edge, find 45 degrees and then draw a line straight through from the corner to the edge of the circle. Mark this as 45 degrees. If you don't have a protractor, simply fold the 90-degree corner of your paper in half, open it up and draw a line along the fold. This will be 45 degrees. You'll then want to cut your clinometer out. Ask an adult for help if you need to. Now punch a hole through your 45-degree line in the corner for your string to go through. Tie a knot in one end, feed it through, and then stick your string to the back of your clinometer to hold it in place. Trim your string so that it is just longer than the edge of your clinometer, and attach your weight. I've used a 2p piece here. Make sure your weight can swing free of your clinometer. Now, to make it easier to use, you can make a sight for the top of your clinometer. Roll some paper around a pen to make a tight cylinder. Use some sticky tape to stick down the edges. You'll then want to stick your sight along the top edge just above your U tree arrow. So use some sticky tape to do this, and then trim the edges off to make it nice and neat. Make sure that the tape doesn't stick down your string. You need that to hang free so that it can swing from side to side. And then with that, your clinometer is finished. To use your clinometer, hold it up at eye level with the arrow for the tree pointing towards the tree. Look through the sight until you can see the top of the tree. Freeze in that position and ask a helper to check if the string is dangling down at the correct angle. You want it to hang right down over the 45-degree line. If the string hangs too close to your face, then you need to move further away from the tree and try again. If the string hangs down too far away from you, then you'll need to move closer. Once you can see the top of the tree through the sight tube, and your string hangs down at 45 degrees, you are now in the right spot. Mark where you're standing with some twigs or stones and measure the distance between you and the base of the tree. Add on your height up to eye level, and these two measurements combined will give you the height of the tree. So how does this work? The clinometer helps us measure out an isosceles right-angled triangle. This kind of triangle will always have one 90-degree corner, which makes it right angled, and two 45-degree corners, with two edges being the same length. This is what makes it isosceles. Once we have lined up correctly so that we can see the top of the tree along the top line of the clinometer and the string hangs down at a 45-degree angle, we know our triangle is the correct shape and we have drawn an imaginary triangle between us and the tree. This means that the side of the triangle that runs from the bottom of the tree to the top, the height, is the same length as the side of the triangle that runs from the bottom of the tree to you. Now, rather than climbing to the top of the tree to measure it, you can simply measure from the bottom of the tree to you and add on your height up to eye level to estimate the full height of the tree. Now that I've gathered all my information about the height of the trees local to me, I can start to sort my information so that I can put it into graph form. Again, I could just leave it as my raw data, but if I want to share my information that I've collected with somebody else, it's much better to put it into the form of a graph. This time, I'm not worried about comparing one part of my data to everything else, but I do want to compare categories. So say I want to compare the height of ash trees to the height of oak trees. To do this, I'm going to use a bar chart. Bar charts are great when you want to compare two categories or more than two categories against one another, but you don't necessarily need to show all of your data. I'll start by sorting my data into categories. I'll sort it by average height so that each tree has got one measurement of its average height. I can do this either on paper or I can sort my data using a computer program like Excel. Now we're ready to draw our bar chart. We're going to start off with a vertical and a horizontal line in the shape of an L like this. Our horizontal line is what's known as our x-axis. Here we add in our categories, so ash, birch, sycamore, cherry and conifer. Our vertical line is known as our y-axis, and on our y-axis we generally put a scale of the things that we're trying to measure, in this case meters. This means we're going to have to write a number scale with even increments in between each set. Make sure you label your scales so that everyone who looks at your bar chart immediately knows what you're trying to show. Finally, we need to add in our bars. The bar will take you up to the height that data point should, so the ash bar should go up to 16, birch to 11, sycamore to 14, cherry to 9, and conifer to 4. You can see the bar chart gives a really clear indication of the height of each tree. You can also add some colours in to make some of the information stand out. As with our pie chart, you can either choose to do this on pen and paper, or you could choose a computer program like Excel to help you. Bar graphs are regularly used by the media to show the difference between groups. One common example is on election night. Media outlets will often use bar charts to show the difference between party results. While watching the video, we've learned about collecting data, the difference between quantitative and qualitative data, and some of the different ways we can display that data, from pie charts to bar graphs. There are lots of other types of graph and chart out there, and you'll probably come across some if you watch the news or some documentaries. A good graph or chart should always have a good title, clear labels and an appropriate scale, but all that is useless if you don't have good data in the first place. When faced with a graph or chart, have a think about what it is the person is trying to tell you or trying to show you, and compare that with what you know about how the data was collected in the first place. Does the way they collect their data actually allow them to answer the question they set? For example, I might make a statement saying that ash and birch are the most common tree in Scotland and use my graph from earlier to back it up. You can see from the graph that ash and birch were the most common trees of those surveyed. But if we take a closer look at the small print, we can see that my survey only consisted of 131 trees in a Glasgow park. Does this allow me to actually answer the question I've posed? Is my data representative of the question I'm asking? There are a few things we can look at to clarify this. We can start by comparing my data to the question I was trying to answer. Now there are millions of trees in Scotland, but my data only looked at 131 of them. For me to correctly answer a question about the whole of Scotland, I would need to count many, many more trees than I did. We would also have to take into consideration the habitats that we surveyed. My survey only took into account one habitat, an urban park. To make my data representative, I would have to collect data from a mix of different habitats around Scotland, from coasts to rivers to mountains to natural woodland, to make sure it represented all of the tree cover around Scotland. Finally, I would also have to consider the geographic scale of my survey. My data came from one local point, which is fine if I want to ask a question about that local area only. However, if I want to answer a question about the whole of Scotland, I have to collect data from a wider geographic range. This would include South Scotland, North Scotland, islands, the highlands, the woodlands, the coastline, making sure that my data represented all of the woodlands across all of Scotland. Even if the data you collected is the right kind to answer your question, a poorly made graph can still be misleading. It should always have the following features: a title that explains what you're looking at, labels that explain the kind of data you are collecting, and a clear scale. Using these three things, we can see from our graph here that ash tree were the tallest tree we surveyed, with sycamore not too far behind. Birch trees were not all that far behind either, with cherry and conifer being the smallest. By manipulating this graph, I can make the same data look very different, however. This graph was made using the exact same data or information that I collected. You can see from this data, at a glance, it looks like the ash tree is much taller than either the birch, sycamore, or any other for that matter. And when we check our three features, our title is still there, our labels are the same, but the scale at the side of our graph has changed quite drastically. It no longer starts at 0 meters but 10 instead. This seemingly small change to our graph makes the data look very different to what it did before, and so it's always worth checking things like the scale on your graph to make sure that your graph is not misleading. That's all from me for the moment. I hope we'll see you back on the estate soon, but in the meantime, if any of you want to have a go at collecting and graphing your own data, then please do so. For those of you who are struggling to leave the house at the moment, then I'll leave some links where you can get your own data online fairly easily. That's all for now. Take care everyone, and we hope to see you very soon.